Hey Tyler, I looked at your quiz and I'm pretty sure I know where your misunderstandings are, so I'm just going to run through two things and hopefully this will help you score better on the retake. But I've got here a picture of a magnet. I've got the north and south pole, and I've got my magnetic field lines. And the field lines form these loops. We say they're loops, they don't really start anywhere, but we'll start at the north pole. And the loop will leave the north pole, go around, go to the south pole, and then it'll go through the magnet right back to where it started, and we get these closed loops. And that's how we visualize the magnetic field. Now these loops do have a direction. The direction, we say that it points away from the north pole. Outside of a magnet, it points away from the north pole and towards the south pole. So that's going to look something like this. Okay, I got some arrows in here now. So it points to the right, and then it circles around, and then points back to the right again when it gets to the south pole. The same with these other loops. They point to the right, they circle around, and then they come back, they point to the right again, and in the middle of inside the magnet, the arrows don't point north to south. They point south right back to north so that we can start back at our loop and complete the loop and get the closed loop. Okay? So this is the nature of the magnetic field and the direction of the magnetic field near the poles. And that's what you need to focus on. Don't worry about the direction out here. We just are focused on the direction of the magnetic field near the poles. So I'm actually going to erase all the noise. So the magnetic field is to the right here, and it's to the right here. Okay, and the problem you were given, one of them had a negative charge going near the north pole, and another problem had a negative charge going near the south pole. Okay, you got the directions wrong and the force directions wrong. So I think you got the force directions wrong because your magnetic field directions were wrong. But I'm going to explain both just in case. So, I don't know what just happened. I'm going to send a charge here up, and it's a negative charge. So its velocity is up, and its magnetic field is to the right. Velocity is up, that's the direction the charge is moving. Then the magnetic field is to the right. For the most part, it's to the right. It does curve a little bit as you get away, but it's to the right mostly. So if the velocity is up and the field is to the right, that means my thumb points up and my fingers point to the right. So thumb goes with the velocity and the fingers go with the magnetic field, and you can see my palm is facing in to the surface. So the force would be in if this was a positive charge, but it's a negative charge. So we have to flip our answer from in to out. The answer is out because it's a negative charge. Okay? And in the other problem you missed, I send a charge down, a negative charge down near the south pole. Now, the direction of the magnetic field has not changed. It's still to the right. So be careful. That can be tricky. What has changed is the velocity is now opposite. The velocity is now opposite. And what you'll get with the right-hand rule, since I only flipped one of these vectors, the velocity vector, the force will also flip. So if I got out for this one should be in. Why don't you try the right-hand rule with this one right now and see that it is in? Remember, right-hand rule is going to give you out, but you have to flip it because it's a negative charge to in. I'm going to hold this up at the screen so you can maybe do a little practice real quick. Alright, so hopefully you got that. Thumb goes down, fingers point to the right, force is out. on a positive charge, but this is negative, so it's in. I hope that helped. Let me know if it did. If it didn't, if you have other questions, just let me know what you need.